Well, hello everyone. I'm just here to demonstrate a few things that we're talking about earthquakes today. And because it's a kind of a larger lecture hall, or we can't all have our individual setups, I wanted to show you a few things that can happen to buildings and the ground in terms of earthquake damage. And of course, there's different things that could happen. And one of the things that we find happening, we don't really think of as the earth, the ground being, with being made of rocks or sediment and soil. That's being very solid and stable. But we know the ground has water in those pore spaces of the rocks or in the sediment and in the soil. And so one of the things that can happen is that this solid ground starts to behave as a liquid as an earthquake starts to occur. So I'm going to take the camera off my face and show you our little setup here. And we have a food storage container, and it's filled with some nice compacted beach sand. And I'm going to place this rock on top there as if it were a building or buildings in this particular area. What I'm going to do is add some groundwater to our container. And that water will percolate down, will infiltrate and percolate down. And what I want to do is completely saturate this sand. And it's moving down pretty nicely. But I want to make sure it's completely saturated. So that may take a few seconds. So earthquakes can have different effects in different areas depending on the type of ground and the type of rock that's in a particular area. And certainly depending on how far you are, how close you are to an epicenter where the earthquake is based, we can see different effects. So this water, I think it looks like we are all saturated. Yeah, because we have some water kind of pooling up on top. So it looks like we are ready to do this. Let me just add a little bit more just to make sure. I don't think anything else is going to run down. So we have a fully saturated sand. Very typical, provided that we're not taking too much water out of the ground for our own use, but that's another story for another day. Now, the building has not been affected. The rock hasn't changed position. I haven't done anything to it. All I did was add water to our container. But if we allow this to experience an earthquake in the form of shaking, let's see what begins to happen actually relatively quickly if this is completely saturated and liquefaction will take place. So let's simulate an earthquake here. Whoa, that was pretty fast. And we don't have to do much more. There we go. Yeah. And now, not only did our rock sink, now imagine if that's a building. And yes, that can really happen to multi-story buildings and not just a single floor. We have to think of that as if it were a 4 or 5 or even a 10-story building, that several floors could disappear, sink into the ground. And that's because that quick shaking that I did allowed the saturated sediment which is a solid with water in the pore spaces, to behave truly like a liquid. And not only did the building sink, but a lot of the water that was in pore space rose up and actually flooded the entire surface of our area. You can actually see, there we go, there you can actually see it moving toward the bottom of the container. And that can happen too as a result of liquefaction. We can actually get new bodies of water, lakes actually forming. New lakes could appear as a result of earthquake activity from the shaking. So the other demonstration I wanted to do is something we call an effect we call in buildings, we call resonance. Now, resonance is actually something you actually don't want to happen. You want it in a concert hall or an auditorium or a theater in order to hear things better, in order for the sound to be amplified. You don't want resonance to be happening in a building. This is my little resonance model, some 2 blocks. I cut some heavy cardstock manila folder to different lengths to simulate buildings of different height, and I put small binder clips on them just for a little bit more dramatic effect, so you can actually see the amplification of the shaking produced by resonance. So a lot of people think or have the misconception that buildings of different heights or the tallest buildings are always to be most at risk. Well, let's simulate an earthquake where the surface waves are passing through this structure, this setup here, and let's see what actually happens when we're moving at about 1 second for one complete wave cycle. And yeah, the two tallest buildings are doing quite a bit of shaking. What I found by shaking it at this particular rate is I found something called the building's natural frequency. The natural frequency means that's the typical frequency that the building will shake anyway, based on its height. Because I've found it with the frequency with which these waves are passing through, we get resonance. That's the amplification of the shaking of the building. And so, yeah, at this rate, with the waves, the seismic waves passing through this speed, yeah, the 2 tallest buildings would be most at risk. But what happens if we speed these seismic waves up? Oh, something a little different taking place there. Now our 3rd tallest building, or the second, here we go. Just got to get that right rhythm there to simulate some real good seismic waves. So that building, when we sped up this entire contraption, showed a lot more resonance. So shorter buildings can also be dangerous places. Now I'm going to have to really work hard to get that smallest building to resonate with the shaking to show just how fast these waves can travel. And there we go. Yeah, you don't want to be in that short building when it's moving that fast. And buildings really can, and the ground really does move that fast when you're very relatively close to the epicenter or the focus of an earthquake. Now, there's lots of things that can prevent buildings from resonating like that. Depending on the types of materials, if it's earthquake proof or earthquake safe, if it has these rollers so that it goes with the shaking, and resonance is actually subtracted so you don't get any shaking at all. You may be looking for things in the interior structure or exterior structure, lots of trusses and lots of triangles. Some of you may know that triangles are the best shape for building, and lots of bridges and buildings have those built into the structure, and they make the building that much more secure and stable. But we want to reduce resonance, so building height, and so when you get resonance happening in buildings at a certain height, depending on the building, some of these layers, the top layers can start what we call pancaking, and that means they start falling down on top of one another, and that was really exemplified in the Mexico City earthquake of 1985. So when I was kind of your age, that was a very, very large earthquake, not all unlike the one that happened just a few weeks ago in Mexico. And we saw the same effect happening. And that has a lot to do with the type of ground that these are built on. These buildings are on which they're constructed. So now we can not only have buildings resonating at different speeds, you can see that, but we can also get liquefaction. So imagine if liquefaction is occurring while these buildings are experiencing resonance. So now we have 2 things to deal with. So just wanted to do those 2 quick demos so you can see 2 of the effects, the types of damage that could occur to buildings and the ground as a result of earthquakes. All right, more later.